Hi everyone, I'm Giulio Costantini and I will show you the basics of R. This will be split in two parts. The first one is the very basics introductory part, and the second one covers a little bit more of handling data. So let's start from the very beginning. What is R? And what is also RStudio, which we will be using in this course. R is an open source version of S+, which is a commercial statistical software. It includes a huge community of statisticians and other people, like psychologists, that write software for doing, for example, statistical analysis, which is the reason why R is mostly used. RStudio is an integrated development environment for R. What does this mean? It includes a code editor. So essentially, your code gets organized better, like colored, indented, and makes the coding process much easier than without RStudio. It allows you to have some facilitating functions, like for importing dataset, which is very useful at the beginning, and includes some other utilities, for example, for creating packages. It's integrated with GitHub, if you know what GitHub is, and it allows creating documents directly in RStudio, etc. Most of these things, of course, will be more relevant if when you will start mastering R a little bit more. But in short, RStudio makes R programming much easier, both at the beginning and when you proceed with learning R. How do you install R? Well, you go to this website and select the version of R according to your operating system. So let's do this for a second. For example, I have Windows. Then you go to install R for the first time, and then you click here and you download R. That's completely free. And then you select the version of R you want, of course. And in the installation process, at some point it will ask you, for example, if you want 32-bit files or only 64-bit, and if you want message translations. My suggestion is to disable 32-bit files. I think that we all have a 64-bit processor. And then disable message translation, which means that when you get an error, it tries to translate it in your language. But that's very annoying because if you have the messages in English, it's easier to Google them when you have a problem. So disable these two options. Sometimes it may happen that if you have a Windows computer, sometimes the folder installation is protected, so that R cannot install programs. If this happens, it used to happen once, now maybe this has been corrected, but if something like that happened, that you cannot install packages, for example, you go to the R installation folder, which in my case is in Programs, then R 411, the latest version, and you click on Properties, and here somewhere you will allow Windows to modify that folder, which could be here, and then, for example, go back here and allow complete control, modify, etc., etc. if it doesn't work for you. Then one important thing is R and RStudio don't get automatically updated, as it happens for some computer programs. So when you have R and RStudio installed, sometimes you need to, for example, in RStudio you go here, check for updates, and now it tells me that I'm using the latest version of RStudio, but sometimes this doesn't happen. So you will download and update a newer version of RStudio, and the same for R. When you type, for example, session info, it tells you which is your version of R, and sometimes this is not up to date anymore. For example, if you go to CRAN and see that now R is 4.2.2 and you have 4.1.1, you have to install another version of R and remove the older version. It's important to keep R up to date. And didn't tell you how to install RStudio. That's not complicated. You go to this link and you here products, RStudio, and then RStudio desktop, and then you choose RStudio desktop, and then the free version. And here you can download the free version here. It automatically selects the one appropriate for your operating system. When you have installed R and RStudio, well, they will essentially work. So when you open RStudio, you will see something like this. You have a slightly different screen if you open it from scratch, in which it tells you the version of R and something about the copyright, etc. Let's try to make this bigger so that you can see it better. So, what is the advantage of learning some R? First, R is free. Mostly people in psychology have been using SPSS a lot as the default option for data analysis. R has the advantage of being completely free, I'd say now and forever. Other software is also free, like Jamovi, for example. R includes all functionalities you can think of. There is nothing that you cannot do with R. SPSS also includes many functionalities, not everything that you would like to have, however. So R is still better, and Jamovi, for example, which is another freely available software, is growing. Its functionalities keep growing, and new functionalities now are added every day, like new packages, new pieces of software. SPSS has a very low, updating SPSS is a very long process, and Jamovi is somewhere in between. You can customize R. So you can, for example, write your own function, write your own package, and if something is not there already, you can do it. That's also true for Jamovi, but it's a little more complicated. And you have to do R coding plus other types of coding. And it's not true for SPSS. I mean, you have some syntax, but it's, quite complex. However, SPSS and also Jamovi are much easier to use at the beginning than R. For doing simple analysis on a simple data set, SPSS and Jamovi are much easier if you have never programmed in your life. R is quite complicated, but when you learn to use R, it opens you many possibilities that you don't have with other software. Also, R is when you want to use syntax, so program yourself some analysis, using a command line, SPSS has this possibility, but this is a matter of personal taste. I hate SPSS syntax because it's horribly complicated and it's completely different than any other programming language. Whereas R feels more like a programming language. So if you have some experience, I don't know, with C or other programming languages, well, R will be easier for you. Jamovi is somewhere in between because Jamovi syntax is actually R. So if you want to use some syntax in Jamovi, that's R. SPSS has some advantages. So SPSS is stable. You have some guarantee that what you do today in SPSS, if you repeat that in a couple of years, you will get the same result. Jamovi, somewhere in between, is slowly updated, so changes in the analysis, for example, are not introduced that often, whereas R is more fluid. So packages can change over time, so it can happen, and it often happens that your code, if you have some code, it is not going to work, for example, as intended in a few years or even a few months. I have an anecdote, something that happened to me. I had this paper under review, and at some point I reran the analysis, and they were different. They were different, and together with Sasha Epskamp, which was my co-author in this paper, we spent like the whole night trying to figure out what happened, and the difference was because one package was updated. But that was not even the package that we were using. It was a package that was used by a package that was used by a package that we were using. So quite complicated. And of course, SPSS and R are extremely widespread. Jamovi, for example, a little bit less, but it's becoming also widespread now. And this is a vignette showing the learning curve of different statistical analysis programs, and this is the curve of R. So the beginning is extremely difficult, but when you get there, and at some point it will be, if you can survive the beginning, R will be awesome for you. It will actually really may change your data analysis process a lot. So what are packages? Packages are a collection of functions together with help files and sometimes also datasets. So in R, you can extend the realm of analysis that you can do using R packages. Some basic functions are already included in the basic installation of R, but most packages can be installed optionally. So you can choose which analysis you'd like to have in your installation of R. Packages are what make R great, because if you need to do something, even something weird, something special, something that you don't think exists, well, it's very likely that someone else had a similar necessity before. So there are thousands, 100,000 of packages, almost for everything. Maybe not 100,000. I think probably more than 10,000. Yeah, R hit the 10,000 packages in 2017, so now it will be, well, something more. I'm not sure how many, but for sure more than 10,000 packages. A package needs to be installed and loaded. So installing means that you download the function, the data, the help files from the internet, and they are installed in your folders. However, every time you want to use a package, you also have to load the package. This is accomplished by using the install packages command, which needs to be used once, and the library or require commands that make the package available in that specific section of R. The only difference between library and require is that require, if the package is not available, returns false. So a logical output that says the package is not there. Whereas if the package is installed, it returns true, so everything is fine. Let's try to install H2020, which is a package that is useful for reading SPSS data. Now, we open our Studio. Now we can go here and ask for a new R script. An R script is just a textual document in which you can type commands, and we write install packages H2020, then require H2020. Then how do you execute this code? You can go over with the mouse, select it, and then clicking run. And then here below, this is the console. We will check more this part in a while. You see some messages. They are red, but they are not problematic. It says that the package has been successfully unpacked, etc., and the package has been downloaded. And then when you ask requiring H2020, loading the required package H2020. So you will need packages throughout this course, many of them, and also when you will work on your data analysis. So my suggestion is, albeit the install package, require library, etc., are good, they work, they are in vanilla R. There is also a better way to do all of this, which is the Pacman package. Pacman is a package which the name is for package management. It's a package that allows you to manage the installation and the loading of other packages. So, of course, the only package you cannot manage with Pacman is Pacman itself. So the first thing we need to do is installing Pacman. And I usually put this code or version of this code in all my scripts. What does it do? Let's check it together. So let's just remove this code for a moment. It's if not, this exclamation mark in R is not. We will also go into that in a moment. If not, require pacman in inverted commas. It says install packages pacman. And then you can do, for example, require pacman or library pacman. If you do this and you execute, pacman gets installed if it's not installed already, and then gets loaded. This is the only package that you need to install and load with these commands. Using this syntax, if pacman is not present, then install it, makes the script better, because otherwise, if you only did this, pacman will be installed every time you run your code. Then, what can you do with the pacman package? Simply, instead of every time asking for install package, haven library, or require haven, install package, I don't know, psych, which is another useful package for psychology, install package psych, you can use only this command, pload, that checks if a package is installed, and if it's not installed, first it gets installed, and then it gets loaded. So, for example, here we have a single call to pload, and then haven, and for example, psych, and here I put this at the beginning of my script, and I keep adding new packages every time I need them. So, and that's it. So, we have already had a quick look to our studio, but let's have a more systematic look at our studio. So, this tab indicates the current file. You can open as many tabs as you want with different code files. For example, I have this, it's called untitled1. I can have another one, which is called untitled2, for example. And I can add other tabs in which I have different projects going on, for example. Then you have, you can ask here, we just saw that, a new file, open file, etc. This is the text editor. So in this window, you can type your code, and your code stays there. It's just essentially a textual file, which gets colored according to what you are writing. For example, let's check our code. We see that the command require and if, so the basics are command are in blue color, the textual string, for example, the name of the packages are in green. If you want, when you write some code, for example, here I made some example, for example, x is equal to 4, multiply 4 by 4, or x by x, and you can run this code in a few ways. For example, let's have some simple code. X equal to 4. Create a new variable, x, and assign it a value 4. Then multiply the number 4 by 4, then multiply x by x, and see that the result is the same. So what can you do to run this code? You can go on a line and click run, 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 and the code gets run below here. You can select it all, click run. Another way that I typically use is to press on my keyboard. I'm on Windows, so Control, Enter. Keep Control down and then press Enter. And the code gets executed directly from the keyboard, so you don't have to go here and run. And clicking run. Okay, if you want, you can also, we will see that later. So, this is the console. So, new commands on a new line. Commands can also be opened, well, they can also be on the same line, but that's not typically done. You can separate different commands by semicolon and put them on, all of them on the same line, but nobody does that. Here you have the run button that we already saw that, the rerun, which reruns the last chunk of code, and the search button, which runs the entire script. This is the console window, so you can type code here and press enter, and the code will be immediately executed. And if you want, if you on your keyboard you press the arrow up, you see the commands that you ran previously. For example, let's go here. If I press the up arrow, I see everything I did before. That sometimes is useful. And for example, let's type the command x plus 2 and hit enter. We get the result 6 because we assign to x the value 4. And the code gets executed, but it doesn't get saved in your script. So here I typically run code that I don't need it to be run later on. Then you can also try typing other operation, etc. So you can use R like a big calculator and do anything that you can do with a calculator. The environment tab allows you to visualize the variables that you have already there, and also as function to import dataset. For example, if you go here, you will see we can resize these tabs. You see x and the value is 4. Okay. The history tab, you get all the code you ran before, and then here you get plots in this window below. You have files that allow you to manage the files in the current directory. You can manage packages, you can visualize help files, etc. So a couple of these windows I won't show you now. So here, for example, the history tab, you see everything that you typed in this session and in previous sessions. The tutorial tab, that's new to me. These other tabs are not useful at the beginning, I will say. Except for the tutorial package, but I've never seen it before. You can try it. The files tab, here you see now I have this working directory, so I have these files in here, but you will see your current working directory here. The plots, for example, if I do plot the number between 1 and 10, you will see that syntax later on. I get a plot visualized here. Here you can manage packages, but I will ask you to manage packages with code. It's a better way to do. The help files, for example, you want to know how does plot work, question mark plot, and you see the help file here. Okay, so some general information about R. Anything that has an hashtag symbol before will not be executed. So if you go to R and want to add some comment, for example here, you put an hashtag and do loading packages, and this string is not executed. Loading packages is just a comment. Inverted commas are used for text strings. R is case sensitive, so a capital version of the same variable is not the same variable. For example, x, lowercase x is equal to 4, uppercase x is equal to 5, and if I type here x, I see 4, and uppercase x, I see 5. Okay, true and false are truth values, so special variables that include true or false. They are uppercase, so you cannot create a variable called true or false. We'll see more of that later. If you don't know something about a function, for example, you can access the help file using the command help, or more frequently the question mark and then the name of the function. Help search for something allow you to make a bigger search for that something. And let's try it. For example, help t-test, and you get in the help tab the help file for the t-test. You can also type question mark t-test, and you get the same help file. It's the same thing, isn't this one? The special symbol for missing values is NA. So NA is like true and false. You cannot create a variable and call it NA, for example. It's not a good idea. And if a value is missing, it's signaled as NA by default in R. Imagine that you want to know all the variables that are currently in your workspace. One way is going to here and under environment see that you have two variables, capital X and lowercase x. You can also do ls, open closed parentheses, and you get that in your environment you have only two variables, x and x. In this one you can use it for any operation you want. If you want to clean your workspace or throw away everything that you have in your environment, you can use this, click here, and then the environment is empty. Now there is no more x. Now let's create again the variables. You can also use the code remove list equal to ls. This special command does the same thing as this one. Clicking this one. The working directory. So I've told you that the files here tab show you the current working directory. You can know which is the working directory using the command getwd. For example, I'm in here, which is not a good place to be. Is another seminar that I gave some times ago. You can also go here and, for example, set the working directory and choose a specific directory. But I typically advise you not to do that. I will show you how to set a working directory in a specific place. You can also set a working directory using the command setwd, or remember that to use the backslash for the foldering in Windows and the forward slash in Mac. But again, you can also do that from here. Session and set working directory, choose directory, or if you save a source file, to source file location, etc. Okay. Basic commands in R. So some very basic commands are getwd gets you the working directory, setwd sets the working directory, ls lists all objects. In this we have seen them. rm, which we have seen in rm list equal to ls, removes one or more objects. For example, if you only want to remove from your environment, let's rerun this. You have small x and big X. If you do remove small x, you only get the big X. So you only remove a specific variable. Then let's see. Well, the help file, we have seen them already. If you have some data, you can visualize them using the commands head or view. We will see that later. And names gets you the names of the variable in some data set. Plus, minus, multiplication, and division are the symbol for basic mathematical operations. This is interesting. You can assign the value to a variable using either the equal symbol or the arrow symbol, the assignment operator. Let's get back here in RStudio. I so far use the assignment operator. You can also use the single equal operator. That's the same thing. But I advise you to use the arrow because, well, we'll see that in a second. The point is that you can also use 2 times equal symbol to inquire whether an object is equal to another object. For example, is x, small x, equal to 4? That's true. Is x equal to 5? That's small x. Well, that's false. So the double equal symbol is not an assignment operator. It is inquiring whether what is on the left is equal to what is on the right. And if the single equal symbol is sometimes confused with this one. It's easier to make mistakes if you use both this and this, but they have a completely different meaning. So typically, to assign values, you use the arrow. Now you can combine. Well, you can also check whether some value, numeric value, is smaller than, smaller or equal than, larger or equal than another value, and you can combine Boolean expression using AND, which is the ampersand symbol, or which is a straight bar, and NOT, which is expression mark. For example, go here. And I somehow forgot to include different from, which is this. Exclamation mark and one equal symbol is asking if two things are different. So let's try with our numbers. For example, is x smaller or equal to 5? That should be true. Is x different than 5? True. I don't know, we can also check is x larger than 5, and that would be false. And we can combine these things. For example, is x small x larger than 5 or capital X equal to 5? And that's true. Or means it's true whether one of these conditions are true. Then also is x equal to 5 and capital X equal to, is small x larger than 5 and capital X equal to 5, and that is false, of course. You can prioritize operations using the parentheses. For example, 2 plus 3 multiplied by 2. If you put 2 plus 3 in parentheses, well, you have 5 multiplied by 2, 10. If you don't put the parentheses, you have 6, which is 3 by 2 multiplied by 2. 3 by 2, to which you add 2, so you get 8. The exponentiation symbol is this one. Abs is for absolute value. The square root is sqrt function, or also you can elevate to the power of 1/2, which is the same of taking the square root. Now, enough of the very, very basics of R. Let's try reading some data. But before that, well, let's talk a little bit about R scripts. So we have been editing this txt file. This is an R script, just a simple text file, but you can typically give it an extension of .r when you save them instead of txt. In this way, when you double click on a .r file, they will be opened by RStudio. Now, let's try to save our current script. This includes some operation and loading some packages. Here is the save symbol. My suggestion is save your script in a folder close to your data. So I typically have a folder named data, and then I put the R script in the folder in which the data folder is, like this. And I call it, this script, we can call it my first R script.r. That's the extension we want. Now, what's the advantage of doing this? Well, first of all, you close RStudio, you don't save anything, but and it got lost. Here it is. So you have your script, in this case called my first, let's make it bigger. My first script. If you close RStudio, and this is very important because it allows you better programming in general. You close RStudio, you have a project, you have a folder, for example, I call it R, in which you have the script and a folder with the data. You double click on this, RStudio gets open. Now, your working directory, you can see it from here, is automatically put in your source file location. That is very important if you want to read and write data, because it makes your life much, much easier. One consequence of having the script where you have the data is that you don't need to specify the path of your data each and every time. You just refer to the folder, the subfolder data. And that makes your code reproducible, for example, on another computer. Otherwise, for example, I give you only the R file, the R folder, but I don't give you all my folders in the computer, and you put the R folder somewhere else. When I open my data, I need to reference to all this path, which is not on your computer, and so makes the code not very reproducible on other computers. So for the moment, just trust me and organize your folders like this. A folder with all the data, and your script, which is in the same folder of the data folder. All right. How can you import data? Well, this is what I just told you. So you create an R file, you save it in the folder in which you have your data. You open RStudio by double-clicking on the file. Now you can use the RStudio importing function and import, for example, the dataset car that we have saved. Let's see how we can do that. Import dataset. Well, the car data, here I put you 3 datasets for you. Cars.save, SAV, BPD, and ANT. .save, for those who recognize it, is the extension of SPSS data. So go here, import dataset from SPSS, browse, go to data, go to cars, open. Now, you could click on this import key and the data will be imported in your environment. But this is not what I want you to do now. I want to copy this code in this code preview. But first of all, you need to ascertain that the data are visualized decently well here, so that you get all your variables and they are nicely separated, etc. This means that the format you're trying to open the data is the correct one. For example, if I could change this, well, it doesn't work, of course. You get this, no data variable, etc. This is actually a SAV file, so the data get visualized nicely here. So you can copy this code, copy code, then hit cancel, then go. I typically load all my data at the beginning of my R scripts. And now, a few things. The first one, library haven. You don't want to use the call to library, so you remove it because you already loaded the package haven here. This one, you can remove it. You load, of course, I haven't run this. I need to run all the package loading part of my code, and then I can hit, and this code gets executed. So I have the data in cars. Here, if I click on the environment, I can visualize those data. If I execute this code, view car, I still visualize the data. So a new tab gets open here. I typically remove also this line, view cars. So the view opens this tab and makes me visualize the dataset, and it's useful. But you don't want it in your script. You want that your script is clean. Otherwise, whenever you run your script, you have all the data you open gets open on the sides. That's not very elegant or good. So I just remove it and I keep only this code line, and I get the dataset cars here. It tells me that there are 24 observations for 9 variables. Okay, so here I remove the call to library in view and I copy paste it in my script. Here it is. If you do view, or you click on the cars object in the environment, you see this. So in this visualization, you cannot modify anything in the dataset. So if you go here in R, it's not like an Excel file. So you cannot change the numbers in here. It's only for visualization purposes. You can also use the command, and I typically put it in below here, head of cars. Head of cars lets me see the first line of the dataset and the first columns of the dataset. It tells me, for example, that the variables are character, CHR, or double precision numerics. These are numbers, etc. You can also ask some summary statistics using the command summary. Let's do it. Summary cars. And of course, this dataset includes several, quite old cars, the length, the baggage size, the weight, horsepower, the tank size, air conditioning, yes or not. Oh, airbag, actually, yes or not. Demand of the car, high demand, average demand, etc., and the price of the car. Well, it tells me for the model variable, it tells me that the length of the number of cars that we have. For the variable length, it tells me the minimum, the first quartile, the median, the mean, the third quartile, and the maximum. And the same for all numeric variables. So it gives me an initial summary of the variables that I have. I can get an idea of which variable has which range, etc. You can also use the dollar syntax to select variables within a data frame. Data frame is how R calls a data set. So for example, if you go here, I would just, all this code that we tried before, I would just remove it. And let's keep the script put in, let's save it. If you do cars dollar, you get this window. This allows you to select between the variables in cars. So for example, cars, let's go to price, for example. We want to know which is the mean price of the cars. We can use the function mean to get the average mean of the variable price that is in the dataset cars. What if we want the standard deviation? SD cars price. We get the standard deviation. In general, well, we also have the median. Let's do it. Median cars price, and you get the median value. You can also use the command scale cars dollar price, and we get scale gives you the standardized variable. So a new variable which has mean 0 and standard deviation 1 calculated from price. Also, what if you have missing values? For example, imagine that you don't have all the values here, but here I have some missing values. You can, in the mean function, compute an a dot remove equal to true, and you get the mean computed after removing missing values. And this is also true for standard deviation and also for the median. You can put this option, removing missing values. This does not work for each and every function. So in general, that's very important for you to know and realize. It will be impossible for me to teach you all the functions that you need, all the options that you may need during your analysis, because those are very different from person to person. My suggestion is this: when you use a function and you want to use other option, go to the help file, for example, median. If you go to median, you see here a description of the function, compute the sample median, a usage of the function, so an example of usage, median of x, and a remove equal to false, etc., etc. And this, what are these? These are arguments, x, and a remove, and these three dots, which are described below here. So what should you put instead of x? An object for which a method has been defined, or a numeric vector containing the values whose median is to be computed. In this case, we used a numeric vector, so it's numbers of which we wanted to compute the median. The option NA remove is a logical value indicating whether NA, so missing values, should be stripped before computation proceeds. You see that here, it does not only tell you NA remove is an argument of median, but also that its default value is false. So if we don't do anything here, if we don't specify anything, it's the same as specifying NA remove equal to false. And these three dots are potentially further arguments for methods, not using the default method. So the three dots means this: if the function, sometimes functions have inside other functions, and these other functions have their own arguments. So these three dots means that sometimes you can pass arguments from a function to an inner function. Well, that's that's a little bit more advanced, but it's good that you know that. Here you get some details of the function. For example, this is a generic function for which methods can be written. This is quite complex. The idea is that you can use different ways to calculate the median according to what you're calculating, the type of object you're calculating the median on. However, the default method, etc., etc., it describes some details of how the function works. For example, you can also calculate the median of dates. And the median for date is, of course, for example, the median value between 1st of January and 2nd of January, 10th of January, and 3 of March. It's not calculated in the same way you calculate the median of numbers. Here, on the value, you get the output that you can expect from the function. On the references, you get the papers on which the function is inspired. And see also, you get other functions that are somehow related to this one. For example, the quantile function for quantiles. And here, very useful, you see some examples. For example, the median 1, 2, 4 gives you the median of the numbers 1, 2, 3, and 4. And this median, if you copy paste this code, the medians, this is a vector of numbers 1, 2, 3. The column means the number between 1 and 3. Then the C concatenates this value and creates a vector. So a sequence of numbers is 1, 2, 3, 100, 1000. And the median of these values is 3. Now, the help file is extremely useful, and to know all the options of a function. Sometimes you have another problem. You have no idea of which is the function that you need for doing something. The best way, albeit R has some built-in search, is to Google. For example, how to calculate median in R. And you see many resources. For example, here, the mean of a dataset, the mean function, the median of a dataset, and you discover that the median is the function that you need. Then you can expect the help file. This works for very simple analysis like median, also for more complex analysis. I don't know how to do XGBoost in R. And then you get some information, a tutorial for doing this machine learning technique in R, for example. So Google essentially is your best friend when you are learning new functions, new options in R, because they are essentially infinite. Now I want you to do this exercise. I will ask you to do several exercises during this course. The idea is that you try to do what I ask you to do without looking at the solution. If, of course, you cannot make it, it's good to look at the solution at some point. But it's better if you try first. You stop the video, you try to solve the problem, and then you check the solution to see if everything is correct. Now, I ask you to import the data and .csv. Be careful because the CSV is a textual format. So, and it's good to know that data are separated by a semicolon. So you can use the reader package and select semicolon as the delimiter. When you try to open it, and remember that you need to load the reader package in the payload code. So when you load all the packages like Haven and Psych, etc. The second thing is you want to visualize the data using view and compute some summary statistic using the command summary. So stop now the video, try to do it, and then when you resume the video, I will show you the solution. Here we are back. Let's make this maybe a little bit bigger. Let's do this together. So we want to import the dataset ANT. Let's go to import dataset. That's textual, so you can choose between base and reader. I suggested you to use reader. Then you browse and go to ant.csv. When you open it, you see that it works. My bad. Data, so even more difficult for you. Data were separated by a colon. I corrected this to make your life easier, not a semicolon. And I didn't correct it in the slide, and then I forgot. So first difficulty for you. If you open it, everything is correct. If the delimiter was semicolon, you needed to select it here, semicolon. And then but if you do that now, you see that all scrambled. The correct delimiter was the default one, the comma, and you can see that the dataset is read correctly. Then you copy this code, it cancel here, you go at the beginning of the file. What do you want to do? put the reader package in the list of pload and remove this line. Run the pload line again to load also the reader package, otherwise you cannot open the data. Then execute this line and you also get the ANT data. Now the view call, as I told you, I typically execute it here. Another possibility is to comment it out. So you put a comment in front of it, you can execute it only by selecting it without the hashtag symbol, and you view the data. But for the moment I will just execute it once and drop it, and then you can do summary ANT. And you have the summary of all the variables in this data set. Now this data, I stole those from another package. The name of the package is easy. If you load the package easy, you have the question mark ANT, you can check more details about the dataset. And yes, you also have help files for datasets. So these are simulated data from the attention network test, and you can see a reference below. You can search the internet and see what this test is. It's just a test for measuring attention. You have the queue, the flankers, grouping variable, and two dependent variables, which is response time and error. I will use this data because it's simple to make examples about several things on using this data. And here is the solution also in the slides. Now, here comes a very boring part. I will go very quick through this part, but it's good that you have some resource that you can go through to check, have some more information about what each variable type is in R. You have already noticed that not all variables are equal in R. So you have, for example, in our current environment, you have that cars is essentially a variable that includes many variables. And if you do x equal to 4, x is also a variable, but they are very different. The cars object and the x object are different. This one includes lots of information, this one includes only a scalar, a number. We already have seen the assignment operator to create simple variables. You can also have the right assignment operator. So writing the arrow in the other direction will work as well, but actually nobody does that. You've noticed that when you create a variable, R does not visualize anything. You need to type the variable x equal to 4. I don't get any result here. If I type x here, I get the result. Okay, and this stuff we already covered a little bit before. So you can use operation on the variable, you can inquire the magnitude of the variable, etc. So x equal to 4 creates a scalar variable. So a variable that has a single number in it. You can also have string variables, a variable that have a textual string attached to it. For example, if you do z equal to open inverted commas, apple, close inverted commas, you get a string variable. You can also have logical variables. For example, q can be equal to true or to false. True and false are actually mostly equivalent to the numbers 1 and 0. So 1 is true and 0 is false, but they are represented as truth values. So scalars, but also string variables and simple logical variables are essentially, in R, they are considered vectors of length 1. So a vector is a concatenation of several elements. For example, if you do head of ANT, each of these variables is a vector. Trial is a vector that includes several numbers, 1, 2, 3, 4, 5, 6, etc., concatenated. Variables in datasets so are vectors, and they can take different classes. For example, trial is a vector of numbers, double precision number, and q is a vector of characters, etc. And the common head, as I showed you before, allows you to inspect the first rows of each dataset and check also the type of the variable of the vector, including in each column. You can also create vectors. There are several ways, and some of those you need to know. The first and most used way maybe is the C command, is concatenation. So C, open parentheses, and something, 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 separated by a comma, close parentheses, creates a vector. Also, C, open comma, 1, 2, 3, creates a vector of 3 numbers. You can also concatenate a variable, a number variable. You can concatenate different variables. These variables can also be vectors. So if x is a vector 1, 2, 3, you can also concatenate x with other numbers. Let's check it. Let's try. For example, x is C, 1, 2, 3, and 100, for example, these numbers. If I now type x, I get this. X is equal to a vector that includes the number 1, 2, 3, and 100. I can also do y is a vector that has 5, 5, 3, then x, then 100 again. If I check what's in y, I get 5, 5, 3, then the content of x, 1, 2, 3, 100, and then 100 again. So the concatenate command is quite convenient. Another convenient command is the semicolon, the colon. So if you do, I don't know, 20 colon 30, I create a variable x that includes the number that go from 20 to 30. I can also use different methods. For example, the command sec from to allows you to create sequences of number. Sequence between 20 and 30, it's the same as writing this command, so with the colon symbol, but the sequence function has more options. So for example, you get sequence from a number to another number by, for example, by equal to 2, and you get a sequence of numbers that are spaced by 2 by 2, 20, 22, 24, etc. You may have noticed that when I go to the help file, I sometimes have the arguments written down. So sequence from equal to 1, 2 equal to 1, by blah, 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 blah. And here I did not tell R that this is actually the argument from, this is the argument to. I just wrote 20 and 30. This works because you can also match the arguments of a function by position. So the first argument that are right here, arguments in a function are separated by a comma. The first argument that are right here assumes that is the first argument of the function. And I can also be more specific and write from equal to 20 to equal to 30 by equal to 2, and I get the same. Why is this important? Because sometimes if you make a mistake, for example, I scramble the order of the arguments. 30, I remove here the first 3 arguments are from, to, and by. And this works. If I scramble the order of those, it doesn't work anymore. But if I scramble the order and I write clearly to which argument I'm referring to, so from 20, by is 2, and 2 equal 30, it works again. So it's good practice when to refer to arguments by the name of the arguments, like this, and maybe also to put them in the same order. Sometimes you don't do that for brevity, and that's okay. So other ways to create arguments, you can repeat using the function rep, and repeat an element as many times as you want. You can generate numbers from a random uniform distribution, from a random normal distribution, and for many other distributions using this function, random uniform, random normal. For example, this command would generate a vector of 50 random numbers from a uniform distribution, which is spaced between maybe 0 and 1. If you don't know, you go to the help file, and it tells that the random uniform, the number of observation, and the min and max, of course, are the limits of the uniform distribution. So it's spaced equally by 0 and 1, and you can change those. You can sample number from a random uniform distribution between -100 and 3. I won't show you the example of all of these functions because, well, there are so many, and I expect that you, at this point, are able to look at the help files or Google them and figure them out yourselves. This sample function actually allows you to randomly sample numbers from a vector. So the vector is the numbers between 1 to 5, you sample 20 numbers and with replacement. Or, for example, you sample 3 numbers without replacement, etc. So you can sample random numbers from a given set of numbers, or sample random objects. This can also be a character vector or anything. Now, you have a vector. You can also label the elements of the vector by giving them names. Let's make an example. This is can sometimes be useful. For example, our vector, imagine that these numbers between 20 and 30 that we created is the age of some friends. You can inquire about the names of these elements. It gives you null as an output if you do names of x, because you haven't set any names, but those will be set manually. You can assign to the names of the vector x a vector of strings that includes the name of each of these objects. I don't know, this could be Tom, let's do Alex, Bert, Christina, Daniel, Emmanuel, Fred, Giulio, name with an H, Herbert, Igor, and John. If I inspect now, oh, then I have one more, Kevin. If I inspect the vector now, it has name attached to each and every value. That's important. Now if I do names of x, I can also get back the names of each of these elements. And well, this will be having names will be important. We will see that in a moment. Okay. Just for you to know, the names are an attribute also of data frames, such as int and cars. So names int shows you the name of all the variables in int. Names cars shows you the names of the variables here, and you can also change those names. So if you do names cars equal to a vector of names, you can change the names of all these variables here. Now, you can also, you can of course create vectors of numbers with concatenate or the other function that I showed you, vectors of character variables, strings, vector of logicals. If you mix up, however, different types of variables, for example, a vector that mixes string variables and numeric variables, R will not preserve the different types of data. For example, if you do this, you will get the 1, 2, 3, 5, 8 won't be considered anymore as numbers, but as letters, as strings. So you cannot use them, for example, to sum this vector to another vector. Okay, then this shows you how you can replace the name of a vector. Also, you can inquire about the length of a vector with the command length. For example, length x, and you get that it has 11 elements. Now, factors are special types of vectors, and they are quite important because factors are used to represent nominal or also ordinal, but mainly nominal variables. So variables, nominal variables in R are called factors. They can be divided in levels. The function factor allows you to convert a numeric or a string vector into a factor. you can check the health file of the factor function for more options. You also have, sometimes in your data frame, you also have variables that are considered or used like factors. Let's, for example, create a variable named gender and with the gender of some of your friends. Let's do it. Gender is equal to male, 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 male. That's it. That's our new variable gender. Here it is. There's length 4, character, male, female, female, male. Well, this is not a factor. Actually, this is just a sequence of strings. If we want, we can convert it to a factor of gender, and we can specify the levels of our, we can, if we just do this, then it's converted to a factor, and the levels are automatically selected. One is female and the other one is male. Makes sense. And it includes the same sequence of values. But now it memorized as a numeric variable, like 1 for female and 2 for male, I think, with labels. Males and female are labels of specific values. Those values are called levels. You can also do something else. For example, create a numeric variable. Let's do this. 1, 1, let's do 1, 1, 2, 2, 1, 1, 1, 2. Then you can convert it to a factor. You specify the levels that are in the variable, in this case 1 and 2, and you specify labels for each of those levels. In this case, the level 1, the value 1 you want it assigned to males, for example, and the level 2 to females. That's it. If you inspect gender, you have a similar result. So males, male, females, male. You can of course change the label without the plural. Male, let's do it again. Male, male, female, female, male, 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 etc. And the levels. So these are nominal variables, and they will be useful, for example, when you perform ANOVA and stuff like this. Now, I am glad that you survived so far. So now let's get to the indexing of vectors. So how can you select elements in a vector? You use in R the square brackets. That's different, for example, for MATLAB, in which you use the parentheses. So you use brackets. For example, you have a vector z. This selects only the first element of vector z. This selects the third element. If you put the minus symbol, this selects all elements except for the element 3. You can also assign a value to a specific element of a vector using this syntax. So the first element of a vector now becomes apple, the string apple. You can also use vectors to select elements of a vector. For example, z of numbers between 1 and 3 selects only the first, second, and third elements of z. The same here. You can also use logicals to select the number of the elements of a vector. For example, a vector of logicals to select the first element of x, the second, the third, but not the fourth, but not the fifth, I don't know, something like this. And you create vector of logicals also by using comparison, for example, Boolean conditions. Let's try this out a little bit. You create, I don't know, we have the vector x equal between 1 and 100. Well, we can select only the first 3 elements of x, and we get the number 1, 2, 3. You can select the elements of x that are 3, 5, and 8. We can change the first element of x, or I don't know, the fourth element of x is now 9. And we get the x gets changed. 1, 2, 3, 9, 5, etc. We can also include, select the elements of x at the condition that x is larger than 3 and x is smaller then 10. And here we get our selection. So we get 9, 5, 6, 7, 8, 9, because they are only these are the numbers that are in X larger than 3 and smaller than 10. This that we put inside here is a condition, is a vector of logicals that we created. If we only take this part and execute it, we get a vector of logicals that tells you, is the first element of X larger than 3 and smaller than 10? No. The second? No. The third? No. The fourth? Yes. Fifth? Yes, etc., etc., etc. Up to the last element of X. You put a vector of logicals inside the square brackets and you get a selection of elements of X. And you can combine these conditions as you want. You can also index a vector by the name of an element. For example, by name of an element. By element names. That's good. I didn't see it in the next slide. So, for example, we had this name vector at some point here. We created a vector X. We recovered this code. We give names to it. We can also do X of birth, and we get the age of birth. Birth is 21. We can get the age of birth. So, okay. If this happens, it's because I hit a combination of buttons, and so don't panic, as there is this combination of buttons that you sometimes click and it only shows you one of the panes. You go to View, Panes, Show all panes, and it gets back. So I can also select, I don't know, the age of birth and Kevin. And here I see that birth is 21 and Kevin is 30. So you can select elements of a vector by name. Okay. So now you try this small exercise. So create a vector called names for names with the names of 6 friends. Create another vector called age with that age, and then select only names of those friends that are younger than 30. And then create a new vector in which those younger than 30 now get the age of 32. It's very, I mean, it's not so simple as an exercise, because you need to figure out that, so here's some help. If you don't want to hear it, just stop and resume. So the help is that you need to figure out that you can also use the age vector to create condition to select elements of the names vector. So try it yourself and check the solution. Okay, I hope that you managed to do it. So the solution is this. You create a vector with some names, Mickey Mouse, Donald Duck, etc., etc. These are Disney characters, a vector of ages. Then you can use the age vector to select elements of the names vector. You can create the new vector age2 in this way. You assign the vector of age to a new variable, you call it age2, and then you, within the age2, you select only those elements that are lower than 30 and you assign them value 32. I mean, that's not so easy because you need to combine what you just learned and try to solve a problem. So this is typically what happens when you use R. Okay. Then in R you have vector operations, and I will go a little bit quick on that because I don't know if we will use those in our course. So percent, multiplication percent is the vector or matrix products of two vectors. And you can also use the matching operator. So the matching operator tells you if an element is included in a vector. The matching operator is percent in percent, and ask, for example, in this line, ask whether the string apple is included in this vector, which is apple, orange, and peach. And if you R is case sensitive, so if you use capital A, this will return true and this will return false. You can also, of course, use the names vector inquire whether the name Mary is included in the vector names. And you can try to experiment a little bit with the matching operator yourself to check how it works a little bit. And well, also with the vector product, and you will see that using this, the product, element-wise product, gives you a very different result than using the vectorial product. So matrices. Matrices are essentially sequences of vectors of the same size. So a table, double entry table. And you can, here I show you how to create a matrix from a vector. For example, the numbers from 1 to 9 can be arranged in a matrix that has 3 rows and 3 columns. And this is by default done by columns. So 1, 2, 3 is the first column, 4, 5, 6 second column, and 7, 8, 9 is the third column. If you specify the argument by row, this is 1, 2, 3 is the first row instead of the first column, etc. You can also use the command cbind, which concatenates vectors in columns. So the numbers from 1 to 10 here are the first column, from 11 to 20 in the second column, etc. Or by rows, the rbind function. And then, unlike vectors, matrices don't have names. They have names for columns, so column names, and row names. Column names and row names work like the name argument of a vector, allow you to set the names or inquire about the names of the rows and the columns of a matrix. And then you can also inquire about the dimension of a matrix. Some of these also works for data frames. For example, if we go here, you can check whether call names of the ANT data, you get the names. Since the ANT data are a data frame, you can also use just names. But this is not true for proper matrices. We will get to data frames a little later. Or you can inquire about the dimension of ANT as well. It has 5,760 rows and 10 columns. And okay, I won't dig too much into matrices and here, but this is actually useful, this part, because it's the same for data frames. So you can select elements of a matrix, but also of a data frame by indexing separately rows and columns. If you use again the square brackets as for vectors, but then you have to specify the rows that you want to select, put a comma and specify the columns that you want to select. It can be one row and one column, it can be many rows, it can be different combination. If you leave something empty, for example, you select the first row, comma, and specify nothing here, means that you are selecting all the columns of the matrix. You can use, again, vectors to select many rows. For example, this selects the rows 1 and 2 of the matrix X. You can put truth values and select on the rows specified and the columns specified by truth values, and you can select columns or even rows by names. Let's try something out. Here, for example, let's go here, and in the ANT dataset, you can select the first 3 rows, the second column, and execute it. And we see that the first 3 participants, the first 3 observations are in the group treatment. You can select it by name. For example, RT is the reaction time, and we can see the first 3 reaction times in our dataset. You can select, let me see, the rows 1, 2, and 1000. That's it. And you can select many columns by putting a vector of names here. Reaction time, I don't know, group, and check if the flanker was here. Reaction time, group flanker for these 3 observations. The first one, the second one, and 1000. So you can select elements, columns, and rows of a matrix in a similar way as what you would do for a vector, but remember you have to separate the selection of columns and of rows using a comma. For example, if I don't specify anything after the comma, let's copy paste this code. I don't specify now anything after the comma, means that I am selecting all the columns. Not all columns are shown here, but okay. Now if I make more space, they are shown. All the columns are shown. So if you don't specify anything before the comma, all the rows are selected. So it doesn't show me all the rows to say, because there will be too much, but it tells me these 3 columns, and then these are all the data with these many more rows. So now that's quite important. You can select columns and rows of a data frame. Okay, now here I show you how to perform matrix operations. But what can we do? Well, you can add, subtract, multiply, divide, and exponentiate numeric elements in a matrix. If you have a numeric matrix, this is also old for vectors. And if you do this, you have 2 matrices of 2 vectors. So you can add, subtract, multiply, divide, etc., and exponentiate a matrix or vector by a scalar. You can also do element-wise product of 2 matrices. This means that all the 2 matrices need to have the same size, and you are multiplying the first element of the first row and column of matrix X by the first element of the first row and column of matrix Y, etc., etc. Second element of the first row, second column element with the first row, second column element of Y, etc., etc. Let's try this out, because it's clearer when you see it. So let's create 2 matrices. X is equal to a matrix including the number between 1 and 9, and row has 3 rows. And Y includes the numbers between, I don't know, 2 and 10, and again has 3 rows. This is matrix X, this is matrix Y. You can, for example, do X plus 3, and you get the same matrix X, but you add 3 to each number. The same if you do X divided by 3, X multiplied by, I don't know, 100, and something like this. You can also do an element-wise multiplication. X multiplied by Y means that you are multiplying, so this is the product of the first element in the first row and column of X and of Y. And then you can check that this is all correct. You're multiplying the second element, this element in X by this element in Y, and you get this result. Specifically, that will be X is 4, this element in Y is 5, 5 by 4 is 20. Different thing if you do the matrix multiplication. You do the matrix product. If you don't know how a matrix product looks like, it's better if you search it out, for example, on the internet or in a manual. What is extremely interesting is that you can use functions like apply or these row sums, call sums. So imagine that you want now select in the A and T data. Let's check them out from a second. We have a couple of numeric variables, reaction times and errors. Imagine that you want to have the sum of all the elements in the reaction time columns or of all the errors. You can do that by selecting the elements reaction time and error in A and T. That gives you all the rows in with columns reaction time and error. And then you can use the command call sums. For example, call sums give you the sum by column of all these elements and the sum by column of all these errors. Similar to that, you have row sums. This is of course not meaningful, but what is number r are just the sum of this plus this, this plus this, this plus this. So the sum of all the elements row-wise instead of column-wise. You can also use, let's copy-paste this code, call means row means. So the mean reaction time is 407 milliseconds, 0.9, blah, blah. And the mean error, so the average error rate is 0.098, so about 10%. More generally, you can apply every function to the rows or the columns of a numeric matrix, also non-numeric matrix, using the command apply. Appliance takes as the first argument the matrix you want to apply the functions to. The second argument is the dimension. 1 is for row and 2 is for columns. Let's do apply to these two columns of A and T, and we apply the command standard deviation, and we get that the standard deviation of reaction time is this, and the standard deviation of error is this one. You can of course apply the function also to the rows, so by row. It doesn't make any sense to do that, but you can apply the standard deviation of a combination of reaction times and error. But the good part is any function, you can apply the compute the median of the columns. What is the median reaction time? This one. What is the median error? This one. Which only means that the error category 0 is more frequent. So this is actually an empowering function for you. It allows you to apply any function to the rows and to the columns of a matrix. Arrays. So arrays are a more complicated concept. I won't go into the details of arrays, but the idea is that they are like tensors. They are matrices that have more than 2 dimensions. For example, a data cube, a 3-dimensional matrix, can be represented as an array. I will leave you the slides, but well, I will not go into the details of arrays. You can look them up if you ever need them. Sometimes they are convenient to use, but it's quite rare for us. Now, the penultimate data type that we will check are lists. Lists are combination of different types of variables. In a list you can put whatever you want. So you can put a vector, a scalar, a matrix, a data set, everything, and include it in a single very large variable. For example, I told you that you cannot combine elements of different types, for example, numeric strings in the same vector or in the same matrix, because they won't be anymore considered as different types of variables. But you can do that in a list. For example, let's create a vector that has, I don't know, 2 strings, cat and dog, a matrix of numbers between 1 and 100 with 10 columns, and a scalar. You can create a list with a command list and combine them all. And then you can name those objects. Let's do this in our studio. Let's create lists. X is equal to a vector including 2 strings, cat, dog. Y, what was it? A matrix of numbers between 1 and 100 with, of course, 10 columns. And then Z is, what was Z? Just the number 4. Execute this, then create a list, we call it a list, is just a list, list of all these elements, X, Y, Z. If I do a list, I have the elements of the list. So the first element, double square brackets, is a vector, cat and dog. The second element is a big matrix of 100 numbers. The third element is just the number 4. And you can put whatever you want in a list. Now, you can also name the objects. For example, let's do names list, R, C, object X, second is object y, and the third one is object z. That's it. If I run this, when I print the list, I see the names of each object in the list. Now, how can you access element of lists? Well, there are 3 ways at least. One way is list, double square brackets, which is somehow different from vectors. And then, for example, you access the first element of the list, which is the vector x. You remember this one? The second element is instead the matrix y. You can also access them by name, for example, object z, and you get this. You can also use single brackets, but if you use single brackets, you don't obtain directly the element. You obtain a sublist including the element. It's slightly different. The most convenient way is, however, the dollar syntax. So you type the name of the list, you type dollar, and R will give you options of all the objects, reminding you of their type. For example, a vector, a matrix, and a vector. So the dollar symbol allows you to access element of a list more easily. This is an advanced function. It's similar to apply, but applies a function to all the elements of a list instead of to the rows or to the columns of a matrix. Lapply applies, for example, this function inquires whether the argument is a numeric variable. Well, if I do lapply a list comma is numeric, I get information about whether each element of the list is a numeric variable or not. Let's try this out. Lapply a list is numeric. And I get that the first object is not a number, the second object is numeric, and the third object is also numeric. These are a matrix and a scalar including numbers. So, why are lists important? When you import a dataset, like ANT or cars that we have already imported, they look like a matrix. If you look at your data here, go to the environment, you take ANT, they look like a matrix. They have columns, they have rows, they are square. But they are actually a very special type of list, in which all the elements have the same length. So the variable subnum, the variable group, the variable block have a different, have the same length. The important property of a data frame is that you can combine in the same object variables of different types, numbers, characters, factors, logicals, and their type is preserved. Another important thing is that you can use, for example, lapply to a data frame. Lapply int is numeric. And you get information about whether each of these elements is a number or not. Each of the elements of ANT. Sometimes you can also treat a dataset as a matrix. So you can also do apply ANT2 is numeric. And you get a similar output. So essentially data frames are somehow in between a list and a matrix. Have properties that are typical of both. So you can create, you can import data frames. When you import data, they are typically considered as data frames. If they are not, you can force an object to be a data frame by using, for example, ANT equal to data frame ANT. Now, many objects imported in R, when you read the data, many functions convert them directly to a table, which is a special type of data frame that is more convenient for certain operations. But typically, data frame is the most convenient data type. So if some function is not working as intended, sometimes you just want to make sure that your data are a data frame indeed. You can create data frames, for example, by combining different variables, importantly different variables of the same length, into a single object using the command data frame. For example, you can try it out yourself. You create a code, A, B, C, D, blah, 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 the letters from the first letters, the gender of each subject, and then you convert it to a factor, and the age of each subject, and you can combine those using the command data frame and save it to an object called myData. You can also you could also use cbind, the command for binding columns, for binding different vectors of the same size and obtain a matrix. You will probably easily see what is the difference between a data frame and a matrix. That the data frame preserved the types of the variables, whereas the matrix, the cbind command does not. Now, how do you index data frames? Well, you can index the elements of a data frame exactly like those of a matrix. For example, the second column can be selected like this, or by name, or you can select the first row, like you would do with a matrix. I showed that before. But you can also address them as the elements of a list. For example, myData$gender only gives you the columns gender. Now let's try with the ANT data frame that we have here. ANT $block gives me a vector with all the blocks, information about all the blocks. I can also do this, like I would do with a matrix. ANT $block, and I get all information about the blocks. I can also use the double square bracket, like ANT block, and that's it. I get the same vector of numbers. So a data frame, so the data that you typically import in R, are, I'd say, data frames, and those data frames are somehow in between matrices and lists. The same notation, of course, myData, for example, $years, can be used to create new variables in your data frame. Now, one last thing, a couple of things, is missing values. The special symbol NA is used by R for representing missing value. For example, if you do this code, think a little bit about what it would do. Well, the solution is it cancels the age of the second observation and it converts it to a missing value. Then you can try it out to compute the mean age of your data frame if you do this, and if you include the option of removing missing value. If you do this, you will obtain, as a result, a missing value. If you do that, you will obtain the mean of the remaining values that are not missing. Well, other information, of course, you can get information about the class of your data. For example, you can do here, class of the object X is a character. Last time we named X as includes cat dog. Class of the object Y is a matrix and an array. So matrices are also a special case of an array. An array is a matrix that can have 3 or more dimensions, but it also have 2 dimensions. I don't know, class of ANT, and we will see that it is a data frame. It is also other things. Table has other specifications, but it's also a data frame. You can also inquire about, for example, the class of variables inside a data frame. Class ANT block is a numeric. Class ANT flanker is a character, etc., etc. There are functions that allow you to inquire about a specific class. So instead of asking in general which class is an object, they specifically ask about, is this a matrix, is this a vector, is this... something else, you can also ask about which element are missing values. You can also try to coerce the class of an object. For example, you have a matrix, you can coerce it to a data frame using the command asDataFrame. Or you have a data frame, you can try to coerce it to a matrix using asMatrix, etc., etc. Now you, using the names and age vectors you created just above, try to combine them into a data frame called neighbors. Select only the rows of the data frame corresponding to colleagues that are younger than 30. Now create a new column in the data frame in which the colleagues are that are younger than 30 are now 32. And optional, inspect the class of the data frame and of the variables within the data frame. Notice that this is not exactly the same exercise that you did before, because it doesn't involve single vectors, but elements of a data frame. So try it yourself, and in the next slide you will see the solution. Here is the solution. You combine them into a data frame using the command data frame. You select only the elements whose age is lower than 30. You can select you can create a new variable within the data frame using the $sign, which is equal to the age variable, and you overwrite the elements of age 2 which are larger than 30, and you write 32 in them. You can print it out. And you can inspect the class of the elements, so class of all neighbors and class of the first, the second, and the third variable. And the last, very last thing is how to save the data. You can save the data in different ways using different commands in different formats. So one of the most widespread commands is the textual command, the comma separated value, the textual format, which is the comma separated value, or CSV. You can use the command write.csv to save a dataset. This command, write.csv neighbors file data neighbors.csv, will save the dataset neighbors that you created above. And it saves it as a CSV file that you can later import using reader. This also uses a few options, like the NA equal to an empty string means that the missing values are not saved with a string NA, but with nothing, which is more convenient sometimes. Just you leave an empty cell. And then row name is equal to false means that there is no added variables for marking the different rows in the data frame. You can also save, let's do that. Let's create some random data. We created this neighbors variable. Just create data frame of 1 to 10. Let's do this. Create a data frame with vectors that I create on the moment, like ed is the numbers between 1 and 10, and then names is the A, B, C, D, E. There is a quicker way to do that, which is using the special variable letters. Is a variable with all the letters, and I take the first 10 letters. This is built in R. So names are just the first 10 letters of the alphabet. So this is our dataset. I can use write.csv of neighbors, and then the file in which I want to save it is data neighbors.csv, and I specify that the missing values are need to be saved as an empty string, and row names equal to false. Row names means that otherwise, if it's true by default, this column here with all the numbers gets saved, the default row names. If I do that and I inspect my data folder, I have this new dataset neighbors. Here it is. It is not well read easily by Excel because our Excel uses the Italian format in which data are separated by a semicolon. If you want that, it's the same, but write CSV2 is another function that saves it in the European sort of format, so they get easily read by Excel if you have the European, I don't know how widespread it is. Whereas write.csv is the American format, which is more used actually. Another thing that you can do is doing simply save. Save saves any object. You can save a data frame, a variable, etc. And the file, or you can also save a list of objects, for example, list, neighbors, and the variable x, whatever you want. And the file must be .r data file. So my data. Let's call it my data. If I do this, okay, doesn't like it. Let's do this. I save the neighbors into an object called my data. Then what happens if I empty my environment here? I remove everything I have. I can then load the file data, my data.data, and I have here the object that I exported. If I have many variables in my environment, for example, now I run all my script, so I get all the computation that I did in the script above, I get them back. I can also use the command save image and specify only the file which you want to save. So my image. This saves everything I have in my environment. So if I clean my environment here and do load file equal to data my image, I get everything back. So this saves in a specific format all the objects that you have in your current working environment. So the advantage of using formats like comma-separated value, CSV, is that they are portable easily on other software. So you can read them, for example, in SPSS, in Excel, in Jamovi, etc. This is a binary format, has some other advantages. So it can only be read and written by R. But being a binary format, it takes much less space on your hard drive. So in this case, that doesn't change much because these are very small data sets. But if you have a very large data set, I don't know, it once happened to be to have a data set that was larger than 1 gigabyte, then if you save it in a binary format, it gets hugely compressed. So you can export data in different formats in R, and you can also export all your working environment. So that's it for the first lecture. Thank you for your attention, and in the next video I will show you a little bit more about handling data in R and doing basic operation on data.